Hello, everybody. How's it going? I'm hoping that your day is going well. Um, it's another opportunity today, and as always, we're going to keep moving forward as there's new things to learn. And so it's important that we do our best, try, help each other out, and see where it takes us. Today, we're going to look at something a little bit different. We're going to look at another way to find volume, and this is kind of by looking at cross sections by adding up a certain kind of cross section of a shape. So adding up cross sections of semicircles or equilateral triangles or squares, and I'll show you kind of what this is going to look like in a second. This is something I know on the AP exam that typically there are a question or two depending on which section that is going to ask you to do something like this. So in the free response or sometimes even on the multiple choice part, there's questions that deal with finding volume using these pieces of cross sections. So today, you're going to take a look at this and see how it works. And so here's what I'm going to ask all of us here's a normal looking shape, and this is just a cylinder. And if I asked you how to find the volume of a cylinder, hopefully you'll say, well, I just need to figure out what the area of my base is. Then what I'm going to do, kind of like we've kind of in some ways been doing, but I just want to add up a bunch of these bases all the way to the top, and I can multiply kind of by that height. So my volume of my, oh, come on, work, good. The volume of my cylinder is just the area of the base times height. And now we obviously know that the base in this case is a circle, so pi r squared times height. But really the idea though is going to be a lot like we're going to do today. You want to find the area of one circle, and we're going to add up a bunch of those all the way across this kind of given height to find our volume. So the formula that you see here for a cylinder is very much like the idea we're going to do. We're going to add up a bunch of these circles, starting at the bottom, going all the way up, and it's going to give us a total amount of volume. This one's nice because it stays the same. Now, if you move forward a little bit, we know what this formula is too, because remember all the related rates questions that dealt with dealt with cones? So what's different about a cone? It still has a base of a circle. But as I go up this time, though, what happens to my circles? My circles get tinier and tinier and tinier as I move up that given height. And in geometry, we learned that, again, it's that base area times height. But then we end up dividing it by 3 is the general formula for it, because you, again, have this changing circle piece as it moves up, and it just so happens to end up working out to be 1/3 times whatever the area of the base is times the height. But in calculus, we can do something similar, and our circles in this case are going to keep changing and changing, moving upward. I don't know if that kind of makes sense, but in my eyes, this is really just the accumulation of these circles. It's just that the circles are changing size. And this is really the general idea of what we're going to look at today. So I'm going to take you here and take a look at this. Here's a visualization, and I found this online, and this is actually the best tool that I could find. It's a little GeoGebra deal. And here's kind of the idea. You can actually pick what kind of cross-section you want. There's 3 in this program to choose from. But let's say I wanted to choose semicircles. What this actually does, it takes this area right here on the left between these two curves, and what it does is says, okay, let's say we have, I don't know, 15 of these semicircles, but what happens over here as I move this slider is, do you see how this is changing this and moving this as we go across? And so what you're actually doing is finding the volume of all these semicircles that would fit between those two functions. Notice that some of them are bigger than others because the function is farther apart, like here. Some of them, though, in the beginning and at the end are really tiny semicircles because the functions are really close together. So It's finding the cross section of using this shape. And it ends up making this volume, and obviously the more of these I put in there, you can see the solid looking shape that has volume that is made from the cross section of semicircles. Now you could choose something else like a square. Now this obviously has a different look. It's going to have a different volume to it as I go across. And again, if you do a bunch of them, it looks kind of cool. But that would be what the shape would look like with cross sections of squares. And squares are probably maybe the easiest of all of them. You'll see in a moment. Might as well take a look at what do triangles look like. So these are equilateral triangles. And so my equilateral triangles, again, let's get a bunch of these as I go across. Look something like that. Pretty sweet. And again, if I have a bunch of them, you can make this thing totally solid and filled in. But this is the idea, though. We're going to take a certain shape, and so whatever that shape may be, and we're going to add up a bunch of them. So the shape has to fit, though, between my curves here and fit that area as I move across. So hopefully that gives you a better visual, because as you know, my drawing skills are very limited, and so I use this idea in your mind to be what it's supposed to look like here in a moment. As I try to draw some of these, and you might try to draw some of these too. Let's do a little bit of this math and see what takes place and happens. I'm going to have you and have us, we're going to go through actually 4 different kinds of cross sections. So we're going to look at squares first, and then later some equilateral triangles, some semicircles, and then maybe even some rectangles. So I want to show you all of them here so you can get an idea of what this is going to look like. So first of all, you're going to be given some functions like you have in the past, like everything else, the area between curves, even volume as we rotate it around an axis. This time we're not rotating it around anything. We're just making and filling it in with whatever cross section that we're given here. And so they're going to say find the volume using cross sections of squares, filling in between x squared and y equals 4. So what's that look like? This is actually what it's going to look like. So here's what x squared looks like. That's pretty simple. And y equals 4. Now as I start to try to visualize this is where it gets hard for me though, but what we're going to try to do is we're going to take and we're going to go across starting at 0 and going all the way up to 4 here. We're going to try to draw squares, and I'm going to try to draw these so these pop out of the screen here. I don't know if that looks like a square at all. Not really. But that's a square that's standing upright. Let me try again. If I drew another one here, it's going to be a lot bigger, a lot bigger square. But we're going to have these squares. I don't know if you can visualize and see these things sticking upright as they stick upward. I tried to draw them sideways so you could see them stick. Oh, that looks pretty horrible. Sorry. And so we want to stack squares. So to do so, a couple things that we need to look at. We're stacking them though in what direction? We're starting at this point and we keep stacking them, going up, going up, going up, going up, all this way, but we're stacking them in the y direction. I don't know if you see that. So we're going up and down in the y direction. And hence, because we're doing that, we're going to need to use y integration. So whichever way you're stacking these things and moving them, that's the type of integration that you're going to use. So we're actually going to use y integration since we're stacking them in the y direction. Hopefully that makes sense. Well, one thing that we're going to need to do, and might as well do it right now, that if we're going to do this in terms of y, if I solve this function, this would actually be the square root of y. So I'm going to write this in terms of y there. And so that function actually looks like that. So, what does one square look like? And so one square, as I look at this, I'm going to call it S for one of these squares. And here's where my drawings here. Let's go back and try to draw another one here. So whatever square that I choose to draw here. it's going to have a base here of this, but because of the way I write this, just this half of it, the way this is written, just this half of this is the square root of y here. The other side of this is also another square root of y. So the sides are to find the area of one square, and I'll use this. So to find the area of my square, it's really like saying I have a side times a side, right? And so that doesn't look good, sorry. It's like saying I have a piece times a piece. In this case, I'm actually going to have 2 of these square roots of y for one of my bases. So maybe if I think of this, let's go back, I'm trying to find a better way to say this. If I want to find the area, it's really base times height. Well, the base of this square is really y and y are 2y. But then what happens to my square as I go up and go over and come back down again, this is also because it's a square, my height is actually the same as my base. And so I'm going to take and multiply that one base times my height. And really what that's going to come out to look like in B, it's going to be, I have 2 of these square roots of y times 2 of these square roots of y, or 2 square roots of y squared, which is really going to give me 4y for the area of just one square. Does that make sense? So again, it's base times height, or you could just say my base squared or side squared, because squares are squares. Now, here's the calculus step. So if that's 1 square equals that, we actually want to make and add these things up starting using y integration, starting at 0, and I'm going to start making these all the way to the top, which was going to be 4, so 0 to 4. Now because I'm not rotating around an axis, there's no pi or any of that stuff, we use a definite integral because that's how you add up things, that's the accumulation of things, and what we're trying to accumulate is just the area of a square. And so if I do so, again, 0 to 4, but again, what is my function? My function is just 4y dy. This is how I find my volume, and so I just have to antiderive. In this case, it's really simple, just the antiderivative of 4y, which ends up being 2y squared. So this would be add 1, get 2, divide by 2, so you get 2y squared. We're going to evaluate at 4 and 0, and guess what happens? I find my volume to end up being 4 squared, or 32 minus 0. I have 32 cubic units of volume if I stack squares between 0 and 4. So all this is really, and again, I personally find this to be easier than some of the things we worked on before. So it's a little variation of finding volume. We're not rotating again around an axis. I just have to figure out, so the hard part is, what is 1 square? The area of 1 square in this problem is 4y. And I'm just adding up then all of those by using a definite integral going in the direction that we want to go. Hopefully that makes sense. Let's try another one. This is probably the harder of all of them, so let's go to the hard one, and we'll look at some other ones in a moment. But what about equilateral triangles? So, same problem, same area here, smash between x squared and 4. This time, though, we're going to try to have equilateral triangles in this. So I'm going to stack these equilateral triangles up, kind of going up. This one's maybe a little bit easier for me to draw. That one didn't turn out too well, but right, we can kind of envision what this is going to look like here, stacking these things together. Now, because we're going to stack equilateral triangles, again, we're going in what direction this time? We're going in the y direction, starting at 0, going to 4. And so this is going to be y integration And so because of that, as we stack them, my function again, just like before, so no change here, x is going to be the square root of y. So in my picture here, if I draw this maybe nicer, you guys have to be laughing at me. I'm laughing at myself right now because my picture is pretty bad. But again, the distance from here to here is the square root of y. And the distance to my other side of that parabola is going to be the square root of y, if I break that apart. And so now for this problem, we want to find the area of one triangle. And if I look carefully, and I'm going to draw one on the side here, so if you remember our properties, but if this is an equilateral triangle, hopefully remember that this is a 60, 60, 60. And if I drew my height down in the middle, this actually makes a 30, 60, 90 triangle. Now back in my picture, if this is the square root of y right here, that's the short leg. So that means that the hypotenuse is going to be 2 square roots of y. The height would be my long leg, which is going to be 3 times the square roots of y. Nope, Mr. Roy, back up. Like I said, it's going to be the square root of 3 times the square root of y, right? That's the rule for a 30, 60, 90 triangle, to find those pieces. So when I come over here and find the area of my triangle, if I think of it 1/2 base times height, I'm going to have 1/2. The base, though, is actually going to be this whole thing right here. So the square root of y, square root of y. So I'm going to have 2 square roots of y. The height is this piece right here using my special right triangle rules, which is the square root of 3 times the square root of y. And if I do all the math now and multiply this all out, my 2 and my half cancel out. I'm going to get the square root of y times the square root of y. I'm actually going to get y right there. And then I have times the square root of 3. That would be the area of one triangle. A little more work on that one to figure out, so using some pieces. So, let's keep going though. If that's one triangle, we want to find the volume. Like before, I'm going from 0 to 4. I just have this area of one triangle. I'm adding those up. So as y changes, my area is going to change based upon what we figured out. If I want to anti-derive this again, maybe you want to pull out the square root of 3. So it's really just the integral of y. Some of you, I'm sure, are done with this, so bear with Mr. Roy, check your work. But I'd actually end up with 1/2 y squared. Evaluated at 4 and evaluated at 0. So square root of 3. If I plug in 4 squared, I'll get 16. But then I take it times 1/2, which is 8. And so I'm going to have 8 minus 0. And actually end up with 8 square roots of 3 units cubed. So, again, hopefully not terrible. But these are the problems that I want us to try and do. Last two, same one here though. So let's try now semicircles. So same routine. Maybe you need to pause the video. Maybe, how about this? If the sub would pause this, how about you guys take a moment, try this. So you need to wake up a little bit, and actually now your turn to think here. You know the process, same function, same area between them, but can you find the area of one semicircle, and can you add those up from 0 to 4? So please pause the video, let them try. All right, how'd you do? So again, my semicircles, these are probably the easiest for me to draw. I got a bunch of these semicircles, I'm stacking them in the y direction. Looks pretty sweet. So as I go again, y direction, my integral in a moment is going to be in terms of dy. I'm going from 0 to 4. That part hasn't changed here because this is the exact same thing. The question now is, how do you find one of these semicircles, what it might be? Again, the distance here is the square root of y. Go back to that. Based upon, again, this function being written broken up, this is going to be x equals the square root of y. And so the distance from there to there is that distance of the square root of y, so going to the outside there. An area of one semicircle will look like this. Well, a semicircle is the area of a circle, which is pi r squared, so you're going to have 1/2 pi times the radius squared. Now, my radius in this case, which that's what I was trying to draw right here, but my radius right here is really just the square root of y. So we're going to have 1/2 pi, but then times what squared? It's going to be the square root of y quantity squared. So if I wanted to now, if I simplify all of this, square root of y squared really gives me 1/2 pi y. That's the area of one semicircle. So did you do this? Did you end up plugging in 1/2 pi y for your volume? And let's quick do the math. Pull out a 1/2 pi, that's my constant, 0 to 4. So really, again, I'm making these easy just because I wanted you to see the concept. You're going to have a 1/2 pi. Now inside, anti-driving, 1/2 y squared. Evaluated at 4 and 0. So if I plug a 4 in, I'm going to get 16. Half of that's 8. 8 minus 0. And so you'll take a look at a little difference here. Half of 8 is 4, so I actually have 4 pi units cubed here when I get all said and done for the volume of my semicircles. Yes? Success? I sure hope so. Now, I know I'm throwing all those, but those are the three basic ones you see a lot of. There's one other one I'm going to look at together with you, and then I'm going to give you the rest of the period. The rest of the period is going to be yours to work in class on some of these types of questions. I'm only giving you two problems, except for there's multiple parts to those problems, sorry. But can we try one more that's a little bit different here? So this one, again, see if you can set this up. This time we're actually using cross sections of rectangles. And the one thing that I should add on here, let me can I type this on here? Let me add this to this. My rectangles, though, are going to have a height of 6 units here. There we go. Does that make sense? Make that stand out for you. So a key little phrase here, I should have typed that in the original. So let's take a little look at my graph here. What's this look like? So this is going to be different now. So if you graph those two pieces, you have your line, which is the green one. You have that parabola, which is going downward as that orange one. And what we want to do now is we want to stack these rectangles between the two functions. And so now the way that it's going to read here, they're going to say you want to stack them perpendicular to the y-axis. And so what that means is that my rectangles are actually going to sit like this. So if I drew it, they're going to go from left to right here. And these rectangles are going to have a height of 6. So they're going to be 6 units tall. I still wish I could draw better for you guys. Maybe I'll draw maybe this looks better. Does that look better? I think so. But these things have a height of 6 though. And, here's the little one right here. This guy has a height, still has a height of 6. He's going to be a little bit smaller, but he has a height of 6. If I drew one here, it's going to be a lot. Again, same height of 6. But can you see those stacked that way? But the way that's going to read, though, is that it's going to read like this. It's perpendicular to the y-axis. And so they're going to go outward from the y-axis like that. That's why they call it perpendicular. So again, the goal right here, and this is the tough part, is you need to find the area of one rectangle. So that's the challenge. That's really the hard part. And a rectangle is just base times height. And Mr. Royk's making this easy on you because I'm telling you the height is 6. And they have to tell you this. It's not like you can do it where it changes. All these, when you do cross sections, they're always going to be, for a rectangle, be given a set height. The question here is, how do you find what that base is going to look like? This base here is different than this base here, which is different than that base there. Those things are changing. And what is, or how do you find the length of that base? Davin, was that? No, that wasn't Davin. Who was it here? Someone said it. Yeah, you just take the distance from the topmost function minus the bottommost function. So this is, again, going back to those ideas we did before. How do you find a length? In this case, you're taking the topmost function, which the topmost one in my case is the orange one. So negative x squared plus 4. And I want to subtract that from that, the bottommost function, which is that. And I'll move this over so we don't get these confused here. So if I did a little more math here, and we have to do some algebra, so if I distribute that negative, it turns into plus x minus 2. And if I do a little bit more, I have negative x squared plus x plus 2. And so my base is going to be all of that. And so I better give myself a little more room here. But the base of my my rectangle, negative x squared plus 2, or plus x plus 2. That's not bad, right? So a little different way to do it. And let's do one last step then. So if I want to find the area of one of these again, I might distribute my 6 with negative 6x squared plus 6x plus 12. Actually, back up. I don't think I will. Let's leave it like this. Because if you leave it just like this, the 6 ends up being a constant. So let's do that. Make our life a little bit easier. And what's my last step now? Oh, and I didn't even mention this. Which way are you integrating here? So which way are you counting your rectangles? Are they being counted in the x direction, or are they being counted in the y direction? Good. So because I'm going from this point to this point, I'm going in the x direction. So my integral is going to be in terms of dx. Bounds this time. How do you find those bounds? Well, this is where I wish I didn't have the smartboard in front of me, but my bounds come from, let's put it right here, I'm setting the functions equal to each other, so you can look at my picture and see it, or if I said negative x squared plus 4 equal to negative x plus 2, maybe I move these pieces over, set it equal to 0, so I'm going to have x squared minus x. If I subtract 4, so minus 2. If I factor that down, you're going to end up with x minus 2x plus 1. So my two answers are going to be x equals 2 and x equals negative 1. And if you look carefully at my graph or your graph, you're going to find that that's where those two endpoints are. But you can always find that by setting your function equal to each other. So our integral is going to go from negative 1 to 2. It's going to be 6 times negative x squared plus x plus 2 plenty squared. That's the area of my rectangle. If you want to pull the 6 out, pull it out. So you're going to pull the 6 out, and my antiderivative is going to look like negative 1/3 x cubed plus 1/2 x squared plus 2x. We're evaluating at 2 and negative 1. If you plug the 2 into this, here's where check our math skills out here. you're going to have a negative 8/3 plus, that would be 4, that would be 2 plus 4, if I plug 2 in, minus, plug in the negative 1, you're going to have negative 1 times negative 1/3, so positive 1/3 plus negative 1 squared is 1, so plus a half. Negative 1 times 2 would be minus 2. Does that look all right? If I get a common denominator, let's see, this one I'll just leave as 3, but this is really negative 8/3 plus 6. Common denominator being 3, so negative 8/3. This is going to be 6 times 3, 18/3. Over here, maybe this one's going to be something over 6, so 2/6 plus 3/6 plus minus 12/6. This is so hard doing this by myself. I always rely upon you guys to shout out what these things should be. Now Jared's shouting it out now, and I can't hear him because he's not here. But 5 minus 12, you're going to get a negative 7/6. Over here, if I add these up, I'm going to have 10/3. If I change that to something 6, should have just done it to begin with. This would end up being 26 minus a negative 7/6, so plus, almost done. You actually get 27/6, but it's times that 6 the whole time. You end up with an area, or a volume, sorry, of 27 units cubed. Nice answer for all this, but that would be my volume given, going back up here, adding up all these rectangles from left to right between the curves. I know this is more information for you, and I know some of us probably feel overwhelmed right now because, again, Mr. Royks not here. He's expecting me to learn new things. How can I move on? But this is where you need to say, hey, I'm going to be in college next year or the year after. I'm going to need to learn to figure some things out on my own, look stuff up. I need to look stuff up. Work with others, which we do a good job at, but we need to do more of that. But I'm going to challenge you today to work with the people around you and work as your class. But I want you to look at 73 and 74 here on page 464. Now, as you write this down, might as well share right now. So there's multiple problems they're going to have you do. Solutions here. 73 is in the book, but 74, if you want to jot this down, I'll write these down. Part A on 74, you're shooting for a volume of 128/3. So see if you can come up with that answer. Part B, a volume of 32 square roots of 3/2. I think that's the equilateral triangle one. Problem C ends up being volume is 16/3 pi. I think that's a semicircle one. And D, the volume ends up being 32/3 units cubed. So take a look. If worth writing those down, write those down so you have a way to check your answers, make sure you're on the right track, and see if you can get to those outcomes. Tomorrow and the day after, we're going to spend some time practicing and reviewing in class, going through not just this, but going back to the rotational stuff, rotating areas around a curve to get a volume, or finding just area between curves, and spend some time answering questions. I should be around in the morning if you want to stop in. I'd love to help you. I am appreciative of your hard work because I know it's hard, and keep plugging away. So that's all you can ask is keep doing your best, but to make use of the time and help each other out. Blessings on the rest of your day. Thanks for your time and attention.